bit. So I should do a sound check for the people on Zoom. Can you hear me? Yes. Okay. Here's a picture of our neural net, or generic neural net. This is the bias neuron. And these are input neurons. We're saying there's n input neurons. And the bias neuron, I put a 1 in there. Always puts out a 1. We can have hidden layers. And then we'll have an output layer. There's output neurons. And as we number, we're going to say, well, the total number of neurons is capital N. So we count 1, 2, 3, 4, 5 at the end, then we keep counting, then we get up to N neurons. That's how big the network is. So there's the total of N neurons. There's N inputs, M outputs, outputs. And then however many hidden layers are the ones in between. And our notation again is that Wij is the weight J to I. And X of I is the output. I and then U sub I is the net input. That's where we add it all up, right? So we've talked about a lot of this before, but I'm just reminding us. All right, so the way that we do the processing is we do a forward propagation and the bias, so that's x0 always sends out a 1. We do that already, that's just how it works. And then for the input neurons, the input just goes on through and comes out. So this is for the neurons 1 to n. And then we do hidden and output neurons. And that's just the standard procedure we do along. You calculate the net input, U sub I. And so this summation just says, okay, we take all of the x's coming out of all the other neurons, multiply by the weight, connecting it together, and add them all up. So that's just how we've always been doing it. And then for just the output layer, we assign the x's, then we call them the outputs O. And the counting here, k goes from 1 to m, as the I goes through whatever the numbers are of this layer on the output layer. That ends with capital N. So as k counts from 1 to m, then I counts from over the output layer. Now notice I wrote this summation here pretty general. I said that all of the outputs from all of the neurons in the whole network get added together, multiplied by the weights up to here. But you know for a fact that in this kind of architecture, we just connect forward, right? So you never have a connection from, say, neuron number capital N, the last one, coming back and going into one of these other neurons. But we can handle that with this because we just make a bunch of the weights 0, and then there's no connection. So we only put non-zero weights in where there's an actual connection. Make sense? So it just allows us to keep it general. So many of the Wij's are 0, especially the recurrent ones where, like this goes from J to I, right? So if J is bigger than I, that means it's a neuron up higher, and so that connection will be 0 because there's no backward connections. Now, if you were going to write a program to do this, you'd probably want to keep track of how many neurons are in the middle layers, and that way you wouldn't do the whole sum, because there's no point in doing the sums that are 0, right? Or the weights are 0, if you want to be efficient. All right, so that's the forward propagation, and that's what we've done in the examples in class. Okay, then the back propagation looks like this. So once that's all done and we got an output, we do back propagation. And the first thing we do is we calculate errors at the outputs. Well, that's nothing new. We did that with our simple perceptron, right? We just calculate the target minus what we actually got. This is a little bit different. We're going to call the error delta. There's the actual target minus the output. So this is the error of neuron K. So like we're picking this one here, and we take the target minus the output for that. That's what goes in there. But then we tack on the derivative of the activation function evaluated as net input. So let's say we're still talking about this neuron. This is that neuron there, neuron number J. This says that we look at the net input UJ going in there. This has an activation function F that we did over there. We take the derivative of that, evaluate it at the net input, and that goes into the formula as well. And that's important because we're going to use this delta in a weight update rule. And really that's saying, well, I need to know what the slope of this thing is, where I was operating, because a steeper slope will cause the weight to change more because the weight has more of an effect. So that F prime in there tells us how steep that neuron is and tells us how to change the weights based on that. And of course we want to change it based on the error, because that's what we did before. If we get an error, we change the weights. If we don't have an error, we don't. Okay, so that gets us the deltas for the output neurons, but remember the secret to this is how do you get errors for the hidden neurons? So this is the secret step that allows neural nets to become useful again. So for the hidden layers, hidden neurons. We calculated delta, but it's done like this. I'm going to write the formula and then we'll explain it. So now we're looking at a neuron. This is our neuron now that we're looking at. So this was J in the formula above, but now we're saying okay, this is neuron number J. Right here, then we're calculating our delta for it. Because we've done all of the J's up here, and now we're coming down to this layer, and we're going to do all of these. And what's that saying? It says, well, this looks familiar. We got the F prime for that neuron. Well, what's this thing? So we're still saying, okay, we want to know what the slope of the F function for this neuron, because that's what we're dealing with. The thing in the bracket, we need to draw a picture for. All right, so let's look at the stuff in here. Here's WLJ. So based on our naming convention, that's the connection from J to L, right? That's just what we said it is. So that's the way from J up to L. And J down here is the one we're trying to calculate the delta for. We've already got the delta for the one up here. And in fact, we have a delta L up here, and in fact, that's what's here. So it says, okay, we have a delta of that neuron up there that we calculated in the output layer. And then this is the way going backward from that to the neuron J where we're trying to calculate the delta. Look at this. This says, oh, hey, add up all of the deltas of the layer above times the weights that go to those. So that's why it's called backpropagation, is we have errors up here. We know these. And we use them multiplied times the weights to calculate the delta here. And in fact, this is the sum over all neurons that J feeds up to. So that's what WJL is. It's all the weights going up. These are all the errors of the layer above. And we simply add this up over all the neurons that J feeds up to. So philosophically, it's saying, okay, I have errors up here, and I'm going to blame this neuron for all of these errors because it contributed to that error. It sent information up, so it was responsible for some of that error up there. And in fact, it's responsible in a weighted way. If we have a really small weight here, and a big weight here, and a really small weight here, it probably contributed most to that error, didn't it? Via that strong connection. So that's why the W gets multiplied by the delta. It says we have an error here, a strong connection, so that error gets assigned down here. Over here, we have a weak connection, Doesn't matter what the error was up here, this neuron probably wasn't so much at fault. So it's really kind of a blame game. Is these neurons are trying to figure out who to blame down here for the fact that they got it wrong. Kind of sounds a little bit like a corporate structure, doesn't it? Or a political environment. Everybody's looking for somebody to blame when things go bad. And it works in this. It says, okay, calculate all the errors based on the errors above. Excuse me. And that's why it works. Because we know the errors up here. Now we can calculate the errors here. And then we can update the weights. All right. Any questions? Are you guys here or are the Zoomers? All right, so you do that for all the neurons below, and then you update the weights. And the weight update rule is going to look really familiar. Because we already have a perceptron weight update rule. The hard part was figuring out how to calculate the errors for the hidden neurons. So then we update here's the formula for that. Set this to K. Oh, I did JK, but that's what I did, so let's be consistent with my notes. This is WJK. And delta W J K. My K down here is C delta J XK, which looks very much like the perceptron rule. With the perceptron rule, we have the learning rate. We have the error. We call it E. And now the delta replaces the error, and it has that F prime thing in it. And then this is the signal along the path. So same philosophy. If we're updating this weight here, along this path, there's a strong signal along that path, then that weight should fall. So that's backpropagation, and the secret is this formula here for the hidden neuron. All right, to understand more about this, we actually need to get into the theory behind it. And the hardest part of it is actually easy calculus, which is the chain rule of derivatives. So let's start. We're still using the same architecture for the neuron or for the network. And to talk about the theory, we're going to define an error function for the entire network. Okay, so here's the theory. We have the same picture here. We have n inputs, n outputs. So we're going to define measure of the network error. Capital E. So this is the squared error summed over the outputs. That's just the total error. You take each output neuron, take the error, sum it. So this is E sub J. So that's the error. How do we get to the weight update rule? Well, this error is a function of all the weights. In fact, you can think of that Wij as a matrix, right? It's a weight matrix. I is the row and J is the column in the matrix. And so this error is a function of all of the weights. And how do we know that? It's got to show up somewhere. The targets are just numbers, but the outputs are calculated based on the weights times the signals, right? So the weights are in here. And backpropagation is a numerical method to minimize this thing, this E. Obviously, the goal would be zero error, but if we can get it really small, that's good enough. So what we want to do is adjust the weights. So we want to adjust the weights W to get them in there. And there's a real simple formula to do that. It's called gradient descent. And the gradient, if you know what that means, it just means the slope. So the slope and descent means going downhill. So it's a method to follow the slope downhill to get to the minimum of E. And that's why we square this, because this is always going to be positive. And we go down a hill until we get zero or as close as possible to it. So gradient descent is a numerical method to go downhill to find the minimum of that. And the fundamental formula is you change the weights to reduce E via this formula. So signaling out just one weight in that matrix, and if we plot the error just on the axis of Wij, it may look something like this. And our current weight here is Wij old. This says calculate the slope. So there's our derivative. That's the slope. And this is the downhill. Because we go in the, listen, I'm drawing a positive slope here, right? So if we go negative, we're going downhill. And the idea is that you'll march a little bit closer to the bottom. And how fast you march is this learning rate C. So it's a really simple concept. You define the error, you take the slope of it, and you go downhill. And you keep going downhill until you get to the bottom. So what's the hard part about this? Well, it's calculating this thing. Because the weights are buried inside O. So that's what we're going to do. We're not going to do it for a general network. We're going to do it for a really simple network so that you can see where this comes from without getting buried in all the notation. Okay, then this. Yeah, E is the function of the O's, and the O's are the function of the weight, so that's where the chain rule comes through. The chain rule derivative to get this. All right, like I said, we're going to do this for a simple network. It's going to have 9 neurons. So I'll draw that up here. And then we're going to calculate this derivative. So here's our simple network. We do this. 4 hidden neurons. And 2 outputs. This is number 1. Number 2. 3, 4, 5, 6, 7, 8, 9. This is going to be O1 and this is going to be O2. O1, O2, O3. And there's connections everywhere, like this is connected to this, to this. And all this is connected here. You can see why we did a simple one, right? So we can draw every single thing in here. And the weight that we're going to use to calculate the derivative, we want to calculate the derivative of E with respect to W51. So that's this connection here. And I did that one because it's one of the ways going into the hidden neurons. But these up here are easy to do. You just calculate the error delta and then you do the weight update. And that's it. So the first thing we do, there's our network, here's the structure. We're going to come up with this error function. So error is equal to 1/2 T1 minus O1 squared plus T2 minus O2 squared. And then we're going to take the derivative of that. Anybody wonder why we put the 1/2 there? It's kind of cool, but that's it, right? All right, well, let's take the derivative. Huh?
Cancel out.
You have an idea? You're going to see in a minute, but can anybody guess? I have an idea.
Beautiful. 5/2 is horizons.
Multiply by 2, when we differentiate, right? Yeah. That's the only reason. Cancels it out. I mean, we could put any number we wanted there. It's we still want to go to 0, so we multiply with 0. Okay, where is W51 in that formula? One of the T's says O1 depends upon W51. Yeah. How about O2? Yeah. So that's the first derivative we get. We get 2 times 1/2, they cancel out. T1 minus O1, and then here's the derivative of O1 with respect to W51 because it depends on it. And here's T2 minus O2 derivative of O2. So far, so good. Now I need the formula for O1 and O2. O1. Yeah, O1 comes out at 8. So it's the activation function of neuron 8. And this is U8. It's the net input of U8 is well, let's write this down. It's going to be W 4 X4 W 5 5. Plus, you go on W 6 X 6 plus W 8 7 X 6. And you can see why we did this nice network that's well defined because we could just write that out and we could look at it. And then O2 is F9, the activation function for that, and U9. And what's U9? It's W9 or X short is W9 5 plus W9 6. 6 plus W9 7. X 7. Where the heck is W51? X5. It's going to be an X5. So in fact, we didn't even really need to write the rest of it, right? But we did, so we can see. So W51 is inside here. Inside here. So the derivative of O1 with respect to W51 is F prime of that, right? We're chain ruling into the function here. Not U, yeah, 8, right? Okay. And then the only one we, and then W85 is here, so we write that. Taking the derivative of what's inside now, and then the derivative of X5 with respect to W51, because that's the only one that depends upon that weight. Yeah, so we're good. And the same thing over here. The derivative of O2 with respect to W51. Again, X5 is the only one that depends on that. And so we get F prime F9. And then the derivative of what's inside So now you can see, well, where does that derivative come from in the formula? It comes from that. The minimization of the derivative, calculating the slope of the error function, gives us that f prime that we had in the formula. All right, so now we got to do this.
Yes. Oh, okay. Okay. Thank you so much.
So what's x5? X5 is W phi 1 times x1 plus W phi 2 times x2 plus W phi 3 x3, right? Just the inputs coming along the signals all added up to give us x5. And then the derivative. This one's easy. W phi 1 shows up right there. Oh, what did I forget? And then this is what we call a U phi. Right? I forgot my activation function. So the derivative is going to be f prime of that thing, and then the derivative of that, what's inside, is going to be x1. So that's what I need there and there. And then this goes up here and here. You following all this? It's a chain rule, but you can see it gets, we have to chain through a bunch. So the derivative here, O1 is what depends on W phi 1. Here's what O1 is. Where's W phi 1? It's inside X5. So that's why we have this. And W phi 1 is inside X5 in O2. So we get F prime inside that. Then we have to take the derivative here. And then we chain roll into what X5 is. There's one of those for X5. So we go ding, 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 ding. There's the actual thing we want to differentiate. So we chain roll into the function there to get that formula. And then when it's all done, we're going to collect it all together. So this up here, and this up here, and this here, and here. And we end up with oh, I made a mistake. Anybody spot it?
Be negative.
Yeah, there's a negative because the derivative of what's inside of this thing is a minus O1, so I really should have a minus in here, right? Now the derivative of this, we get 2 out here times this, negative derivative of this with respect to W phi 1. My bad. So we have a minus P1 minus O1 times, and then putting in there, we get F prime A. U8, we get 8.5. This thing up here. So that's the first term up there. Then we have T2 minus O2 with the minus sign, correct? Now we're doing this, F9, W9.5, this thing here. That all looks good. Then we notice we have the same thing here. Here. Let's hold on to that. In fact, we can factor that out. We can factor it out and start collecting stuff together. But let's start reducing the complexity here. Let's name some things. Let's name this That's gonna be a different story. And this visible. Marker. Yeah. Let's name this delta 8. Because it's the error in neuron 8. There. Let's name this delta 9. We could call it anything we wanted. We could call one George and Edwin Henry. But the name delta 8 is more related to what it is. It's the delta or the error delta of neuron 8 and neuron 9 with regard to its targeted output. And we collect the F prime to go along for the ride. So let's combine that together now. Let's factor this out, call these by their new names, and see what we get. Right, so I factored that out. Use my new names. Can you guys on Zoom see that okay? The blue. I see it on my screen. Is that showing up okay? Not complaining. So either they like it or they fall asleep or they're cooking dinner. Maybe somebody's having something good. All right, so look at this. This is the error delta at 8. This is the error delta at 9. And then that's the weight here going up there from the neuron we're talking about. So that's the sum of the errors in the neurons up here weighted by the weights that went up there from the neuron we're trying to adjust. So this we're going to call, you guys have a good name for it? Oh, I want to have this in too. I'm going to call that delta 5. Because it matches the way we define the deltas here. We included the F prime. And so this is the errors coming back down from the neurons above times the F prime of the current activation. And then this is the signal along the path. And so the weight update rule is the gradient descent thing. Notice we get a minus and a minus. It simply says update the weight. Sorry. 5-1. 5-1 based on the gradient we just calculated. We flip the sign. And that says all you need to know to update that weight is you need to know the delta associated with that and the error goes on the signal that goes along the path. And if we wanted to update this neuron, we need to know its error delta and the signal that goes along the path up to it. So if you name these like this, and this was the thing that Wellhart and McClellan popularized, is they said, hey, name these things like this, And then you can just calculate deltas all the way back and use this simple formula, and you're good. So you don't have to remember all the chain rules and derivatives and all that. All you do is calculate the deltas according to the formulas. You have to have these derivatives, but that's just that function. And so it's a nice, neat structure where the x's go forward and the deltas go backward with a very similar formula. And it goes downhill on the error surface, that E, and so you get as close as you can to the bottom, and you know your error is small, and you've learned. You do that for all the training pairs. You put training pair in, inputs in, outputs out, calculate the error, go downhill, put another training pair in, calculate the outputs, go downhill, and you keep doing that over and over again. A lot like we did with the perceptron. But now we can deal with these hidden neurons here. All right, that's one of the more technical lectures, but I think it's important that you can look at it, go home and look through it again. Because if you understand this, then you understand how backprop works and why it works, because it's really just going downhill. And we'll talk real quick about some issues with backprop, and then I'll let you go. Days like these, I'm sure you guys have all seen Star Wars, right? There's the one that was in Star Wars, the second Star Wars, Empire Strikes Back, where they're on the frozen ice planet, right? And Luke's stranded out into the tundra, and the sun's going down, and the temperature's dropping, and they close the blast doors, right? And everybody thinks he's dead.
There's the part where he cuts open an animal.
Yes, exactly. Yeah, and then he says he gets warm, and then Han Solo goes out and finds him, saves his life. That's right, isn't it?
I don't think so.
But there's also some animal that grabs him and puts him in a cave. Is that the same? I need to rewatch that. It's been a long time. We're going to watch it in here.
I always remember the animal scene because it's a tauntaun, but he cuts it open and all its guts are clear.
Yeah, and that's what warms him up because it keeps him warm. Oh, it's Han Solo that then finds him and cuts the tauntaun open and puts Luke in there to save his life. That's right. Yeah, after the animal drags him into the cave. All right, we got this now. I do know the first three that came out in sequence were really good. The next three that came out that were prequels to all that weren't so good. And then the latest ones I think are pretty good. You know, you're not as big a fan of the latest ones? No. And I broke down because of the pandemic and everything else, and we paid for Disney Plus. So we can watch The Mandalorian, and it's a great show. It's fun. Okay, so problems with backprop before our Earth turns into the ice planet. So we've talked about this error surface. So again, let's just say we're only looking in one dimension, and the error is on the W51. And let's say it looks like this. Make that go all the way down really close to 0. Like that, right? But let's make this a little flat over here. So let's say we pick an initial weight before we start training that's like right here. This algorithm goes downhill on the error surface, the derivative. So you calculate the gradient. You're going down this way, you don't get stuck in that crack. What's going to happen? If you take little tiny steps downhill, you're going to end up at what's called a local minimum. You never get to the global minimum want to be at, where the error is almost zero. So that's one of the issues. You can get stuck. In a local minimum. So there's several fixes. One is start with big steps and reduce. You can see how that would work, right? If we start out with a high training rate, initially, it would go and maybe shoot past that minimum. It would get over to here just because we took such a big step. But we can't keep taking big steps because if we do that again, then we'll end up over here and then we'll take a big step and it'll tell us to go back this way. We might bounce out. And that's what you guys saw from the homework is too large of a learning rate for too long. You just end up bouncing back and forth. So the software that I'll show you how to do, I think next time, starts out with a large learning rate, but then it reduces the learning rate as it goes along, so that once it gets in the big minimum, it's going to bounce its way down to the bottom and get there. The other fix is, notice I've only drawn just one dimension here. But with this network, we actually have a bunch more weights, right? Here's W73, all of these other weights. So those are actually axes in another dimension. And maybe this minimum here only looks like a minimum here, but it actually goes downhill if we go into the board. So if you add more weights, there may be a path to still keep going downhill in other dimensions to get down to here. So the other fix is to add more neurons and more weights or more parameters, so that there may be a parameter that will get you to the minimum better. Now you guys have all studied curve fits, right? And, you know, where you do linear fits to data and higher order polynomial fits. So you can kind of think of this like that. It's not a polynomial. It's a function instead of the polynomial coefficients, but it's a function of these different weights. And with a polynomial, the higher order the polynomial, the more complicated data you can fit, right? But if you remember, if you have data points like this, and you're trying to do f of x versus x, and with a polynomial, if you do a linear fit, you're going to get an average through here, right? If you do a second order fit, it's going to try to fit some of this variation. If you do a really high order fit, you're going to get really weird stuff that goes to exactly every point, but obviously maybe doesn't look like the function that really ought to be. Maybe it's a linear relationship. There's just noise in the data. So the same kind of downside happens here. You have to have enough neurons to match the data that you have. But if you put too many in there, then you can get weird fits of the data. This tends to be more robust to that kind of thing happening than polynomial fits because they're such simple functions that are used. And there's a lot of schemes that add and subtract neurons in and out of a network automatically to try to fit the data. But fundamentally, if your data varies, like with a third or fourth order function, you've got to have enough parameters in your network to map the data. But if you put too many in, then you got too much going on, and it may not do as well. So you can get stuck at a local minimum, but you can add more neurons, more parameters, and it helps you model. And then another fix for this is you can just do what's called jogging or bumping the weights. So you do little steps down here, you get stuck down here, and then you can add a random number to the weight with the idea that you might bounce yourself out of that minimum and then you keep going. There's a bunch of other bells and whistles. As we learn the software that does this, I'll point out what they've done to help deal with this kind of an issue. And then next time, we'll talk about a bias neuron. I've been drawing that bias, but we haven't said why. It's to fix that problem that you had with exercise number 3 in the homework. The only way to get that 0, 0 input to give a 1 out is to add a bias neuron. And I'll show you how that works next time. On Blackboard, I put a handout called Building a Simple Backpropagation Neural Net in NeuralWorks. And that's the software we're going to use. So I'm going to demo that next time. So pull up that handout if you don't want to print it out, because I don't know, it's like 50 pages. Bring it as a PDF on a laptop or something where you can look at it. And we'll go through that. I'm going to demo the software in here. It's pretty easy to use. It's point and click, but you just need to know what the different points and clickings do for you. So make sure you grab that handout before next time, because we'll get to that. I'm also going to post another homework assignment on Blackboard, so look for that. Comments, questions? Somebody in the chat said something. Can kind of see the blue. All right, so I switch back to black. Look for homework, pull up the handout. Oh, I told my other class, both my classes are Monday, Wednesday. If you've been watching the forecast, not only is it going to be cold on Monday, but there's a chance of snow. You never know in Kansas, we could get 10 inches or we could get. If for some reason the weather is bad on Monday, watch your email. I might email you and say, hey, the weather's really bad. I'm just going to teach over Zoom. So watch for that. I don't want you to waste the trip if you're going to be not here. But I will definitely send you an email by noon telling you whether we're having class or Zoom. Okay? Stay warm. Have a good weekend.